function. Now, of course, I can show that to you as an image again. What's that going to look like? Well, you probably figured this out because you're all so smart. It's just going to be a blurry version of that image. Okay? And I'm showing it here side by side with the blurred function, or sorry, the smooth function, right? Because there is this direct analogy between what we call blurring in the image and smoothing of that function. It's exactly the same thing. So here's a quiz. All right? So an image can be thought of as A, a two-dimensional array of numbers ranging from some minimum to some maximum. B, a function I of x and y. C, something generated by a camera. And D, all of the above. Okay, so probably pretty obvious it's all of the above. Now I'm going to tell you most Georgia Tech tests are a little bit harder than that, okay? But it's just to get you to pay attention. So let's talk a little bit more about images as functions, all right? So we can think of an image as a function, f, sometimes we'll say f, sometimes we'll say I, that maps, from r squared to r. That is, it goes from an xy to some pure intensity or value at that position xy. But we're not going to have sort of arbitrary functions. We're going to limit them in certain ways. For us, an image is going to be defined to be over some bound. So x ranges from a to b, and y ranges from c to d, and the intensity ranges from some min to some max. Now, raise your hands out there if you think that image values go from 0 to 255. Come on, be honest. You're raising your hands, okay? That is a pure accident. 0 to 1 probably would have made a lot more sense. 0 be black, white be white. Oh, sorry, 1 be white. Where did the 255? Well, you computer nerds, we all know. Well, there were 8 bits in a byte, right? So if they're all on, they're all ones, we'll call that 255. There is nothing special about 255, okay? And in fact, later we're going to even have to have images that can have negatives in them. So the thing that you just have to remember is we're going to allow our images to go from some min to some max. The min will be sort of the blackest black. The max will be the whitest white if we're actually thinking of them as intensities. But later, if we think of them as just pure functions, like image derivatives, they're just going to take on some real value. By the way, we can do color images the same way. Now, instead of having one function that maps x, y to an intensity, we just have 3 functions, often called R, G, and B, sometimes called L, U, and V. We're going to talk about that way later. All right? But basically, you can think of this as what we call a vector-valued function. So every pixel, the function is a vector of 3 numbers. Like I said, most of the time, we'll be sticking to gray-level images.
Now, how is this a function? Well, you can think of an image as a collection of light intensities at different locations. For instance, this area on the shirt is pretty bright. Here, this shadow is dark, and this grass somewhere in between. Now, how would you identify these different locations? Note that these locations are laid out in a 2-dimensional space. We can characterize it using, say, an x-axis, which is the horizontal dimension, and a y-axis, which is the vertical dimension. Any location on the image can thus be specified using an x-axis value and a y-axis value. Notice that this x-axis value can be any real number. Similarly for y. Now the image intensity at the location x, y can be written as f of x, y. And that's how you can think of an image as a function. Now what about the intensity values in the image? If we assume that they are real numbers, then we can say that f is a mapping from r cross r, or r square, to r. Now this definition seems to indicate that images are infinitely large. But practically speaking, images have a finite size. They have a certain width and a certain height. Assuming that our coordinate origin is here, we can define numerical bounds for the image. For instance, 10 to 210 on the x-axis, and say 15 to 165 along the y-axis. We also know that image intensity values have a finite range. Say in this image, they range from 0 through 10. Given these finite ranges, how would you define this image as a function? Complete the function definition above by filling in the boxes. Note that the first pair of boxes is the range of column values. The second set of boxes represents the range of rows or Y values. And finally, the third set of boxes represent the image intensity range. The answer is fairly straightforward. X values can range from 10 through 210. Y values can range from 15 through 165. And we define the image intensity values to be in the range 0 through 10. So, a color image is also a function. It's just that the value at each location is no longer a single number that represents the light intensity. Instead, it can be a vector that holds 3 different intensities for 3 color components. For instance, each location in an RGB image has values for red, green, and blue. These values can be separated into 3 different channels or planes. If you take all the red intensity values in an image, you have your red plane. Similarly, if you take all the green intensity values, you get your green plane. Likewise for blue. Given this scheme, where each location is associated with a tuple of 3 values, and assuming that each of these intensity values is a real number, and so are the values for X and Y, how would you represent this image as a functional mapping? Mark the expressions that correctly represent the desired functional mapping. Let's first look at the range of the function. Since each location has a tuple of 3 values, hence the right-hand side of the mapping should have r cross r cross r, or r cube. The first expression is therefore clearly wrong. Note that a color image is still a mapping over a domain of 2-dimensional x and y values. Hence, the third expression is also incorrect. Therefore, we can represent an RGB image as a mapping from r cross r to r cross r cross r. This is the same as writing r cross r maps to r cube. In fact, you could also shorten it to r squared to r cube.
So far, we've talked about functions from a mathematical perspective, but this is a computer. And in a computer, everything has to be digital, and that gives us even some more restrictions, okay? So let's take a look at the grid that was a little chunk taken out of the Phyllis Diller picture. So here you see, in fact, I had a little MATLAB code, right? It says PD, Phyllis Diller, that was my array. And this says rows 40 to 60, columns 30 to 40, and that's the middle of Phyllis's face. You might not have known it, that's the middle of Phyllis's face. By the way, one of the things you should realize is this is exactly the same representation as the picture on the screen. But you happen to have a vision system that will look at bright dots and dark dots and see things. And when you look at these numbers, you don't immediately see those things. Mathematically, these are identical. Oh, and by the way, something that I just mentioned, which is going to bite us in some place. These are rows and these are columns. Rows go down, columns go over. So X and Y, Y, okay, remember that, we're going to do that now. In digital images, in computer vision, we typically operate on discrete images, right? And that means we have to do 2 types of discretizations. First of all, we have to sample the 2D space on a regular grid. That is, we have discrete pixels at locations. You know what pixels stand for? Picture elements. Okay? In the old television world, that was called PELs, also for picture elements. But computers, we have to be special, so we call them pixels. Fine. So we have to pick them at specific locations. The other thing is we have to quantize each value. We don't get to have a continuous real value. We have some finite number of bits to represent that. So like we said, maybe you have 8 bits, so it'll go from 0 to 255. These days, you tend to have 16-bit images, or 12-bit, or depending upon the device. But the idea is that it's quantized to some level. Even though it's quantized, later we're going to tend to think of these things as floating point. And I'll tell you now that if you compute with integer images, like unsigned integer 8 bits, your code will just break. So use floating point images. So in general, especially in MATLAB, which we'll be doing a lot of, images are represented as a matrix of values, typically integer values to start with as an image. So here's Phyllis, looking as delightful as ever. And we index our matrices by, again, I and J, row and column, sometimes X going over this way and Y going that way. If I say some pixel IJ, it means row I, column J. If I say some pixel at XY, all right, XY, X is horizontal, so I have to go get the column that, so you'll have to swap them. And part of the problem is our math is always determined by X and Y, and our computing is always determined by I and J, row and column, and that's a tension that we'll have. Sometimes we use 1D signals. 1D signals will just be an array of numbers as well. All right.
Let's take a moment to talk about image size. Here is an image defined over a two-dimensional space. Since it is a finite image, it must have certain bounds. Let's say the limits along the x-axis are 10 and 330, and similarly along the y-axis 20 to 278. Can you tell me what is the width and height of the image? How about the area that it occupies? Type in your answers in the boxes provided. That's right. The width is the difference between the two x-axis limits, 330 minus 10 equals 320. Similarly, the height is 258, and the area is simply width times height, and that comes out to 82,560. For digital images, the height is the same as the number of rows, and width is the number of columns. Thus, the area is the total number of picture elements or pixels. Now, if each pixel has 3 color values for red, green, and blue, a color image, specifically an RGB image, has 3 different values at each pixel. This means a color image of this size has 82560 times 3 total color values. If each color value is represented by 1 byte, then you need as many bytes to represent the entire color image. This should give you a sense of how much memory you need to store an image on a computer and how it depends on the width, height, and number of color channels.
Most of you, I hope, will use either MATLAB or Octave for the work in this class. We talked about how you can use also Python and OpenCV, etc. MATLAB, or the open source version of it, Octave, makes it easy. If you're an actual student somewhere, really registered somewhere, there's a student edition of MATLAB. It is less than most textbooks and a great thing for you to purchase. So in MATLAB, images and matrices just work really well. So, here's all it takes to read an image, right? So we've got this function imRead, and we're going to read in, there's a file, peppers.png. And by the way, if you don't put these semicolons in there, MATLAB spits out all the numbers, which is incredibly painful. And then what we're going to do here is, I'm going to take just the green channel. And the green channel can be indexed, because in MATLAB, images have a certain number of rows, a certain number of columns, and you can think of this as the color planes or the layers. So when I say IM of colon, that means all the rows, comma, colon, all the columns, and then 2, that's red, green, blue, so that's green. Now, some of you are screaming, no, Professor Bobick, you messed up. I will certainly mess up in this class, although I will mess up less frequently in this class than in my in-class class. Why? Because Megan hates to see me mess up. That's actually not really true. She likes to put it in there, but anyway. No, unfortunately, I did not mess up. Or fortunately, I don't know. MATLAB indexing starts at 1. In sort of normal computer, 0 would be red, 1 would be green, 2 would be blue. In MATLAB indexing of arrays, it starts with 1. So 1 is red, 2 is green, 3 is blue. That means we all the time have to be subtracting 1 off of indexes in order to be able to multiply them to get into other locations. The computer scientists out there will know exactly what I'm talking about. Just remember that MATLAB is 1-based indexing. So we've got our green channel, which is just a single channel. Well, I can just show that, and if I call IMShow, we'll talk about that in a minute, well, green has just got a single layer, so thinks of it as a grayscale image, and IMShow in this case would just display it. And then you'll notice MATLAB makes it really easy to plot things also. So it says draw a line, and can you see that red line in there? It just drew a line right across there. Ain't MATLAB great? In fact, I can also just call plot. So what this says give me the 256th row, give me all the columns, and then plot it, and you'll just get a plot. By the way, I recommend highly getting used to sort of exploring your images, plotting the values and being able to see is what's going on